The purpose of this video is to discuss a thermal mixing case study. This case study investigates the geometry of a T-junction duct where two gas streams meet and a flow structure is formed there. My name is Jeff Franklin. I am the primary architect of Azore CFD. Please visit the website azorecfd.com to learn more about that CFD tool. If you would like to contact me, you can contact me through LinkedIn or using my email address. Let's get started talking about this case study. To start our exploration of this geometry and flow structures, I thought it might be a good idea to start by looking at fluid path lines. And what fluid path lines represent would be if you would grab onto a molecule of the air, for this case study it's air, and watched where it went. And here you can see right here these fluid path lines or tubes, and if you grabbed one of the molecules and followed it, it is represented by these tubes. And in this particular case study, there are two gas streams meeting at this T-junction, and one of the gas streams is cold, kind of represented by these blue line tubes, and then another gas stream which is hot, which is represented by the red path lines. And some of the flow structures that are kind of obvious from this animation are that the cold gases are kind of pushed out of the way by the hot gases. Notice how they bend out of the way here. The other flow structure that's kind of interesting to note here is that as the hot gases come up and push the cold gases out of the way, you'll notice right here this little recirculation zone where the flow kind of makes a little tumbling motion here. And those are some of the flow structures that we're going to look at in this case study in more detail. So I thought maybe we'd start with just an outline of what we're going to talk about here in this presentation. We're first going to review kind of what is the geometry of the test fixture, how is it set up, and then we're going to take a look. We should probably have a good idea of kind of the flow structure. We looked at the path lines here, but we're going to look a little bit more closely at what we might expect in terms of temperature gradients. And this is a turbulent flow problem, so maybe we'll have just a little bit of a discussion about what turbulence means and how it might impact our predictions in this geometry. And when we're done with that, we'll look at how we set up the CFD model. What is the geometry specifically? What are the boundary conditions? How do we set up this model? And once we're done getting familiar with that, then we're going to kind of look at CFD predictions, and we're going to do some comparisons with the experimental data that we have. And we're going to kind of do a smattering of different tools. We're going to look at two different software packages, Azore CFD and ANSYS Fluent, and we're going to look at two different turbulence models, the K epsilon turbulence model and the K omega SST turbulence model. These are two equation turbulence models that are very commonly used. So we're going to kind of look and exercise these CFD tools and compare the results to experimental data and see what kind of predictions we can get out of that. And then when we're done with that, we'll have maybe just a quick summary and discussion about what we saw. So the experimental apparatus is shown right here in the top, and it's basically kind of a setup. The air is kind of forced through this T-junction geometry, but it's kind of conditioned before it gets into the T-junction to manage the turbulence, to make the predictions easy to, not very affected by the turbulence in there. And so what it really starts with, over on the left-hand side, we have a fan. And so the air is kind of drawn in and forced through this system right here. And after the air comes out of the fan, then it's expanded in this diffuser section. And then it is forced through a honeycomb structure, and then through a kind of a contraction right here. And then it is introduced into the T-junction ductwork. And so you can see right here, this horizontal section is the cold airflow that's coming in here. Then we have the branching flow that comes in, and that's our hot gases, and it also goes through a kind of a contracting section here. And so the air is treated as it passes through here, and it's treated with 2 screen meshes and a honeycomb, which is shown right here, plus 1 more screen mesh right here at the exit. And that's really to get the turbulence treated, kind of get the turbulence to a low level. And then on the branching duct right here, we also have a screen mesh at this portion right here. If you're interested in more detailed information about this apparatus, the reference for this benchmark and all of the test data can be found here at this, using this reference down here. So our CFD model, the geometry that we're going to use to represent that is shown right here. And what we have here is we're going to start our model right at the beginning of the contraction. And so right over here, this is where our cold air is going to come in, and this is a representation of that contracting section. And so for the hot air, we're going to start right at the beginning of the contraction as well. And so here are kind of the fluid properties. The air coming in is going to be at 12 degrees C. We have a mass flow rate, and the turbulence values that we're going to use on the inlet here is we're going to assume a 10% mean kinetic energy and use the dissipation rate set using a hydraulic diameter of 0.01 meters. And similar boundary conditions will be used down here for the hot air, 60 degrees C, a mass flow rate, and the same turbulence boundary conditions. For the fluid properties, we're going to assume that the density is variable with temperature using the ideal gas law. The viscosity we're going to assume it's constant, as well as the specific heat and the thermal conductivity. And those values that we chose are right here. For the geometry of this model, you'll notice that it's a very symmetric geometry. So to reduce a cell count in this particular case is we're going to only model half of the model, half of the geometry, and we're going to cut it in half right along this symmetry plane right here. We're going to assume that there are no heat losses from the walls. So all of the energy that only will be coming in is through the gas stream at each one of these locations. No other energy will be introduced. And here is that reference again for this information. And so now we need to kind of pick some coordinate systems, and those are shown over here. And those coordinate systems we're going to use when we look at the experimental data about where we are and where this data is taken. And so for the coordinate system from top to bottom in this duct, in this horizontal section, we're going to choose our y coordinate to start right at the very bottom of the duct right here. And we're going to call that our y coordinate. And we'll measure information in a y direction as it goes up from the bottom of the duct to the top of the duct. For the horizontal duct, we're going to start our coordinate system just to the right of where the hot gases are introduced. And we're going to call that our x coordinate. And that will travel from there to the right in the flow direction. The flow is going to be coming in from the bottom right here. And you will notice we're going to pick a nominal velocity, this u0, and that will be used for non-dimensionalizing our velocities for looking at the experimental data. We're going to use a b value, so the width of the duct right down here is 30 millimeters, and we're going to designate that as b. And we have the width of the duct right here is 60 millimeters, and we're going to designate that as h. Our u0 value is 3.87 for the velocities that we have chosen here. So that outlines kind of the setup that we're going to use for putting together our CFD model. The mesh topology we used a hexahedral mesh, just over a 500,000 cells. We're going to target a wall function of about, or a wall y plus of a right around 15 to 20. And that is kind of the method that we're going to use to resolve the turbulence near the walls. You could see here the hexahedral nature, and I've kind of refined our view in this area because it's kind of all black, so we can kind of see what the mesh looks like in that area. It's a very ideal Cartesian mesh. It's flow aligned, and this should sufficiently capture the flow structures that we're expecting in this geometry. So before we jump into looking at the CFD results, I thought it would be a good idea to kind of get an idea of what we might expect in terms of the flow structures. And the reference here has some experimental visualization that we can use to kind of get familiar with those flow structures before we look and compare it to the experimental data and our CFD predictions. So let's just take a look at that. So this is an image that was taken from our reference here, and what we have here is an oil mist visualization that's captured through a laser sheet, and this is an instantaneous image of the flow structures right here. And this is kind of at a center line in our duct, and what we have here down here is where our hot gases are introduced. And when the hot gases are introduced, they introduced it with some oil mist. So you can kind of see this grayish area is that oil mist, and this would be kind of where the hot gases might end up in our duct system when it meets with a cold gas stream that's coming over from this direction. So the black area is essentially our cold air, and this grayish area is our hot air. And here are our non-dimensional dimensions of where we're going to look at it. And we have some experimental data that we're going to look at. And here, this is that X over B. So the B is our width of our hot air duct. And so we're looking at distances, kind of the width of our hot duct downstream here of 1, 2, 3, or in the negative direction upstream. And one thing to notice right here, because we have these turbulent flow structures, you notice that it's very irregular, and you can kind of imagine this changing all the time. And you could see here, here's our cold air, but maybe kind of look right down here, you can see where the turbulence has really kind of transported a portion of this cold air all the way down here. And this is probably moving. So the turbulence is playing a fairly major role in mixing these two together. And so we're going to look at that some more. So it's good to have a good understanding of this, how turbulence really affects this mixing process. So here's another view, and I like this view because it really shows the flow structures and how erratic they might be. So what we're looking at here is another image, and the colors are a little bit different in this image. In this image, the colors, the light color is our cold gas stream, and the dark colors are our hot gas stream here. And so right here, this is kind of similar to the image we just looked at. Here are our hot gases coming in and our cold gases. But if we kind of look right here, we're going to look down the duct now. Right over here, we can kind of see an image of how that mixing process happens right here. And you can see that it is very irregular because of turbulence. And this is an instantaneous image, and the frame rate that they used to take these images was at 250 frames per second. So you can see that this is irregular. We assumed, for our CFD simulations, we're going to make an assumption that the flow structures are symmetric about this line, and you can kind of see from this image that instantaneously the flow structures are not symmetric. They're similar all the way across. But if you could imagine that after you would average all of these together, you're probably going to get something very symmetric across here. And those are the assumptions that we made when we put our CFD model together. But you can really see these turbulent mixing. You can almost see that is an eddy right there, where the flow structure is coming in and doubling over. Really kind of see these eddies forming here. So I find this a very enlightening. I think this is a good representation to give us a feel for turbulence is really important in order to capture that mixing process of the cold gas stream and the hot gas stream. So we can see that these flow structures along here are important in order to capture the mixing process here between the cold gas stream and the hot gas stream. And that is typically kind of captured using what's called a turbulence model. And there's a poem here that was written by this fellow Lewis Richardson, who did some original work in turbulence, and it helps describe the kind of the purpose of a turbulence model. And the poem goes like this: big whirls have little whirls that feed on their velocity, and little whirls have lesser whirls, and so on to viscosity. And I think this is a good kind of way of describing the purpose of turbulence models, because turbulence models want to capture turbulence. And in this image, we have a, kind of a very detailed image, and we see these whirls or eddies in here. But the thing that this image does not capture is that there is likely even smaller whirls here in this area that we cannot see. If we could take an even more zoomed in image, we would likely see those whirls as well. And that's one of the aspects of turbulence modeling that makes it very difficult to model all of the physics that are going on there, because the smaller whirls have even shorter timescales. The timescales for this flow structure that we happen to capture and we can look at in here is still pretty rapid, because the picture was taken at 250 frames per second. And so that makes capturing this flow structure and representing it numerically quite challenging. And there are some people that are actually doing that, and it's a technique called direct numerical simulation. And in those, it's trying to capture all of the whirls right here at the big length scale all the way down. And so then really you're only left with the viscosity representation there. So you're kind of directly solving the equations, Navier-Stokes equations. But though, that requires some significant compute resources, and so there's only a very limited set of problems that can be solved using those methods because of the limitations on the compute hardware that's necessary in order to do those types of simulations. And most practical engineering problems are turbulent, and they cannot really be kind of represented using this direct numerical simulation method. There are, more and more problems as computer hardware gets more powerful. You can do more and more problems, but most practical engineering problems are not, cannot be simulated using that method. So what do we do? How do we kind of span that? And we use this turbulence model right here. And for our model, I've kind of overlaid the mesh length scale that we're using for the benchmark that we're going to be simulating, because we're looking at a steady state representation of all of these whirls here. And you can even see at this mesh length scale, we are not capturing. You can see some of these whirls are just kind of passing right through this, so we wouldn't even be able to capture this flow structure even with this mesh length scale. And perhaps we could make this mesh a little bit finer, and we could probably capture the eddies that are shown here, but probably not the smaller eddies that are below this. And so how do we represent that? And what is commonly done for a lot of two-equation turbulence models is you come up with this thing called turbulent viscosity. And this turbulent viscosity is a scalar field that in essence kind of tries to kind of represent this process without actually resolving it. And so that's the purpose, and we're going to look a little bit more closely at the turbulent viscosity and how we calculate that. Or not really how you calculate it. I have a number of other videos out there, and they'll be down in the description for this video if you're interested in the actual math, but we're just going to talk a little bit in general terms about this turbulent viscosity concept. So I thought it'd be a good idea to kind of look at this scalar field, this turbulent viscosity scalar field. And so what I have done here is I've taken the prediction of the turbulent viscosity based on the K epsilon turbulence model, and I have plotted it here. This is right at the center line of our T-junction, and this is the prediction of the turbulent viscosity there. And you could kind of see red areas are high turbulent viscosity and blue areas are low turbulent viscosity. So the red areas kind of represent the area where there are a lot of whirls and the whirls are very strong in nature. And the blue areas represent where there are fewer whirls or these eddies and they don't have very much strength. And so you could kind of look at these colors and say that the turbulent mixing, the effect of turbulent mixing is very high in this area. There's a lot of mixing due to turbulence in this area, and there's lesser mixing in this area. And we could kind of use that to kind of mimic the behavior of the turbulence, but not actually resolve it. And so how is that kind of taken into account in the energy equation? And in the energy equation, we kind of change the thermal conductivity of the fluid when we solve the energy equation, and we use what's called the effective thermal conductivity. And I thought the math for that is kind of done like this. What we do really is kind of take into account, and we take the laminar thermal conductivity and we add an additional correction term here that has a few terms in it. It has this mu T is our turbulent viscosity, and our Cp is the specific heat, and then we have a turbulent Prandtl number, which is kind of a correction for turbulence. We can't really get it perfect. This value is not exactly what we want, and so we have an additional correction. And people have found that a value of right around 0.85 does a good job of representing it. And so let's just think about this a little bit more. So here's our turbulent viscosity, and you can see that when this value is larger, the effective thermal conductivity is going to be higher. And if we remember our fluid path lines, they were kind of traveling kind of in this direction. And when we make our thermal conductivity higher here, that means that the effect, the spreading perpendicular to our fluid path line, is going to be greater. So that's kind of giving the impact of our turbulence, but we're actually not resolving it. And so it makes a certain amount of sense right here that when our turbulent viscosity is high, then our effective viscosity is going to be high. But likewise, and kind of as a poem says, when this value becomes small, then we kind of trunk down to just the laminar representation. Having the specific heat in there is also kind of makes a certain amount of sense, because the specific heat really kind of represents the thermal capacity, how much energy can be moved around or that is present in our fluid. And so right over here, you can see when you have a higher thermal capacity in your fluid, then it will have a larger impact, and we want to have that effect in here. So that's kind of the math there, you know, the algebra that is performed by the CFD tool. But I thought maybe it'd be interesting to just do kind of go through a sample set of calculations. So if we were to look right over here and look at this color right here, we could go down to our color bar and we can pick a value out here. So we'll pick this value, we'll put it in here. So that's our turbulent viscosity is this value. Then we'll multiply it by our specific heat and then divide it by the turbulent Prandtl number. And then we add it with our laminar thermal conductivity right here, and we get a value of right around 0.5. And you'll notice that that is much, much larger than the laminar thermal conductivity, like almost 20 times more. So you can see that turbulence is playing a very major role here in what the mixing process that we're trying to represent, almost to the point where this maybe matters a little less, not that it's not important, but this is the dominant thing that is affecting our representation of turbulence in this area. So now we have kind of an idea of this turbulent viscosity, but let's kind of see its impact. And I thought maybe it would be good to take a look at a CFD prediction here. And here we're going to look at the temperature prediction for the K epsilon turbulence model right at the center line of our duct here. So in our CFD prediction, the red areas represent our hot gas stream and the blue areas represent the cold gas stream. And so this is a steady state simulation. So we're looking at an average value of what the temperature would be in our domain after these two gas streams merge. And right down here for reference, I have put the kind of an image at that same location, this test data image. And so we can kind of look and compare where, like basically we see down here, this is the warm gas stream, and this is the warm gas stream. We can see this interface here. But you'll notice that there's a very kind of smooth transition between the cold and the hot as it progresses along here, and it's not very irregular shaped. And that's because our turbulence model is doing a lot of averaging there, and that's the purpose of the turbulence model, is to find an average value there. So we kind of get an averaging effect. So we can see, if we remember, we looked at this dark spot down here, which represents how this cold gas was transported way down here, and that means that there is kind of a cold area there. And we can kind of see that in this image as well, where the temperatures over here are lower than they are for the total temperature that is coming in here. And so this gives us a flavor for what's going on here. You can also see right along here on this path, there's a distinct line between the cold and the hot. And you can also see that the CFD model predictions also show that very distinct line between the cold gas stream and the hot gas stream. So you could see this does a fair job of representing, if you imagine this moving and our whirls dying and shrinking and you average them all out, you could kind of see how this temperature distribution, this smooth temperature distribution, is a fair representation of what you see kind of instantaneously right here. So now let's talk about where the data is going to be taken in here. They have collected data along these lines, and here we have our X over B lines here. And so there's data taken at these distinct locations here, and I've kind of overlaid these lines here with the total velocity. So here is the total velocity predictions. The hot air is coming in here, the cold air is coming in here, and the experimental data, averaged experimental data that we can use to compare to our CFD predictions to see how we might be able to predict the actual experimental data. We can compare to these lines right here. And this is a total velocity prediction right at the center line. So we also have some lines across there, and I thought maybe we could look at the temperature distribution with respect to these lines right here. So let's just look down in here. So right over here is kind of a little isometric view of the ductwork and the temperature distributions, and we're going to kind of pick some cutting planes right in here and look at the temperature distribution on those cutting planes. So right up in here you can see right here, this would be like the wall side of one of these cutting planes, and this would be along the center line. And the experimental data that they gathered, they have data right along the center line, and then they have actually a number of lines in the reference, but I've chosen, just for this purposes, we're just going to look at the data along the center line, and then we're going to pick a line close to the wall on the right-hand side here of this image. And that is kind of an interesting one because you could kind of see the interaction of the wall here. So, but I thought maybe it's kind of interesting to look at these flow structures for the predictions of the temperature here, and you could kind of see where the hot gases are coming in here, and that's represented by the red colors, and then the cold gases are represented by this blue area, which is our cold gases. But I've overlaid the velocity, kind of the fluid directionality as well, and you could kind of see the flow structures. Here you can see as the cold air is coming in, it's kind of being pushed out of the way, similar to what we saw with the path lines. So you can kind of see the velocity vectors going up. And you can also see here where the hot gases are coming in, and they're being pushed over, and you can see this little recirculation zone that we saw in the fluid path lines early on right here forming. And so now we could kind of look along here. And so if we were to kind of take a cutting plane right here and look down, that would be this image right here. And you could see the distinct line where the cold gases are up here and the hot gases are right here. But you also see that the velocity is kind of going upward right here in this area, generally speaking. If we move down to this plane right here, we can see that, this line has gotten higher where the distinction between the hot and the cold. But you also see that their flow structures are starting to change because of this recirculation zone. We're getting a little bit of secondary flow, meaning that the flow is actually going side to side in the ductwork right here. That's forming. Now, if we go a little bit further down, we're right here, we're kind of in the middle of this recirculation zone, and we can see that this secondary flow structure has developed pretty significantly. So we kind of have some rotational flow right here and a secondary rotational flow here. And what that is having a tendency to do is this rotational flow is having a tendency to draw some of the cold air down into the hot air area. And you'll notice also this rotational structure is having a tendency to pull the hot air into the cold air right here. And you can kind of see how that this wall effect and the secondary flow structures are spreading out the flow in this area along here. So that's kind of, so we have a lot of lines here, these magenta lines, to look at in terms of our experimental data. So let's look at our parametric simulation. So we're going to look at two software tools. We're going to look at Azore and ANSYS Fluent. And we're going to look at our two turbulence models, the K epsilon turbulence model and the K omega SST turbulence model, which are two very popular turbulence models that are used for predicting turbulence. Okay, this is the first slide where we're going to compare the experimental data to our CFD predictions. Over here is a view of our geometry. And these magenta lines show where the experimental data was measured at a steady state. So we have these are the lines along the center line, and these are the lines close to the wall. And so we're going to look at the experimental data there. So for the first bit of data we're going to look at the normalized axial velocity. So that's the velocity that is traveling kind of horizontally in the duct right here. And if you remember previously, we had this reference velocity U0, and we will use that to normalize the velocity, the normalized velocity component along here. And the normalization, basically we're going to take the local velocity at a particular location and divide it by 2 times this U0 velocity, and that should give us a value somewhere between 0 and 1 that we can compare to, and the experimental data was gathered and presented in that way too. So now these line plots, and what these line plots attempt to do is kind of visually show the velocity profile along the duct right here. And so this top, we're doing a measurement. So we have y over h. So this is the distance from the bottom of the duct to the top of the duct. And that would be, so for instance, at this location right here, this is at -3. So that's this location right here. And so this point right here is this point right here on our graph. And this point right here is this point right here on our graph. And this kind of shows the shape of the velocity profile. If we imagine that this line right here, and the distance between this line and this line is the velocity magnitude. And you can kind of see, if you look at down here on the x-axis, this is the magnitude our normalized magnitude right here, and so we're seeing values on the order of 0.5. So you can see the distance between here and here is the magnitude of the velocity. And as you get closer to the wall, you can see that the magnitude of the velocity is getting smaller and smaller by this graph. Now the lines in this graph here, let's just quickly talk about that. The experimental data is displayed using a line and a little circle. So that little circle kind of represents where the measurement was actually taken. And the line kind of shows how these are connected together so that you won't get confused between maybe a dot right here in this set of data and a dot over here in this set. I mean, it's kind of obvious here, but over in these, it might get confusing if they weren't connected together with a line. And we have 4 other sets of lines here. We have one set that is green, and we have another set that is blue. And so the green set of lines are predictions made by Azore CFD, and the blue set of lines are the predictions made by Fluent. And so then the lines are different shapes. So like this line is solid and this one is dashed. And that kind of is a distinction between the K epsilon turbulence model. So you can see that the green solid line is the Azore prediction for the K epsilon turbulence model, and the blue solid line is the Fluent prediction for the K epsilon turbulence model. The dashed lines are for the K omega SST turbulence model. So we can use these lines to compare between like a particular software and turbulence model prediction and the experimental data. So let's just pick one of these lines and look at it. So let's just pick this line right here. And this line's kind of interesting because you'll notice that some of the measurements right here are behind our reference line. And when they're behind the reference line, what that really means is that the velocities are going in the opposite direction. And so that's basically, we're in that little eddy that we saw in the fluid path lines. And the velocity vectors, you can see this is where the velocity is going in the reverse direction. So basically on this line, we can kind of use this to look at the differences between a software package's prediction and the experimental data. And of course, when the line is closer to the experimental data, that means that the prediction quality is better. And when the line is further away, the prediction quality has degraded some. And so, for instance, the solid green line is Azore's prediction of the K epsilon turbulence model, and the dashed green line is Azore's prediction with the K omega SST turbulence model. So you can kind of go along here and look at how the turbulence model and the CFD software package in general is able to capture the flow structures along here. And some of the data is right on in this area, because right where these two gas streams meet, it looks maybe relatively close to the experimental data. There's not visually much difference, whereas down in these areas, there is some departure from the data. Okay, so now we're going to move to a line right over here that's near the wall. So, and this is the distance. Basically, this is a non-dimensional distance. A value of 1 would be right on the wall, so we're just off the wall. And these are the velocity profiles along the wall. And you'll notice right in here, this is probably the most challenging portion of this geometry because you have the wall effects and also that recirculation zone in that eddy. So here is probably the most challenging portion based on the departure from the experimental data and the CFD predictions. So now we're going to look at the comparisons of the temperature to the experimental data. And just like with the velocity, we're going to use a normalization technique to get values between 0 and 1. And here is the equation that we'll use. We'll basically take the local temperature minus the reference cold temperature divided by the difference between the hot and the cold temperature, and that'll give us values between 0 and 1. And what that really means is that areas that are 0 are cold, and areas that 1 are hot. And the same line plots, the same coloring is used to distinguish between the software packages and the turbulence models. So right over here you can see upstream of the, where the gases mix, you can see that they're all of the data and the CFD predictions say that it's all cold, which makes a certain amount of sense. And then as you get down here, so this is right after the two gas streams meet, and you can see that at the top of the duct, it is all cold, and at the bottom of the duct, it is all hot, and you see some transition between the hot and the cold, and this is that mixing area that we were seeing, and this is where our turbulence is playing a role in predicting how that mixing process occurs. So we can kind of make a comparison between the experimental data and the CFD predictions along here. So just like with the velocity, we are going to now look at the lines very close to the wall, and you'll notice that the lines where they took experimental data for the temperature is actually closer than where the velocity was taken, and here it was taken at 0.917. And you'll look right in here, you'll notice that there is a noticeable departure from the experimental data in our predictions for CFD. And some of the other things that are kind of, I find interesting is even right in down here, you'll notice that the temperature down here, even though it's right downstream, you would think that this would be all hot. And right over here, you'll notice also that the CFD predictions, since we assumed that the walls were isothermal, there was no heat loss, that the temperature there is all hot. Yet the experimental data seems to indicate that either the turbulence is drawing in some of that cold air into this area right away, or perhaps maybe there's a little bit of energy loss. Maybe the test fixture itself is not completely isothermal. Because you'll notice all along here that the experimental data seems to indicate that the temperatures are lower than the hot gas stream where you would think they were there. So it's unclear whether or not it's from the turbulence model or from the experimental data. You'll also notice that this, right in here, this knee, there's pretty marked difference between the two. And you might say, well, maybe that is the temperature, or perhaps the turbulence model is letting us down in this area. It's unclear. So now we've looked at the experimental data, so we see that turbulence is important there just by visually looking at the flow structures. And we've looked at the comparisons, our CFD predictions, and how well it compares to the experimental data. But before we finish this discussion, I thought it would be kind of good to look at the turbulent viscosity specifically and what its flow structure, this scalar value looks like as we go down the duct. And so what I've done here is I've taken some cross sections at our different locations along the length of this duct, our X over B locations. And right over here, just a reminder, on the right-hand side, this is our wall side, and on the center line, that's the center of our duct. And so the top set of plots here is the K epsilon predictions of the turbulent viscosity, and the bottom row is the K omega SST predictions. And there's a number of observations we can make about this turbulent viscosity. You'll see here that we know that the turbulent viscosity is low at the beginning because we have all those screens and everything that we controlled the turbulent structures in our fixture to make sure that they're low. And so you can see right here, this is where the two gas streams are meeting, and so our turbulence is beginning to form. Our turbulent flow structure is right where they begin. So here is the shear layers between these two gas streams when they meet right here. The top it's low, the bottom is low, but then it's higher right here. And then as you progress down the duct, we have the turbulent viscosity even gets larger, so our turbulent structures are growing even more because we're starting to approach that recirculation zone, and so our eddies are forming. And then as we progress even further down the duct, we see that our turbulent viscosity down in this eddy area is continuing to grow and grow as we progress down the duct. We'll also notice right at the top, where there are no shear layers, or right at the very top, that the turbulent viscosity remains low. The other thing that is kind of interesting to look at here is, our turbulent viscosity in the center of the duct is larger because there's nothing limiting the rotational motion of these whirls or eddies. But as you approach the wall of the duct, you'll notice that the turbulent viscosity begins to drop very rapidly. And that makes a certain amount of sense because now these whirls, these tumbling flows are striking the wall and they're dying out. And we see that happen in our scalar field, our turbulent viscosity that's trying to represent this behavior. So that all makes a certain amount of sense. You'll notice that the K omega SST turbulence model follows the same pattern, low at the beginning, higher at the back or at the end of the duct that we're looking at here. In where the eddy is, you'll see that it's a larger value. The other thing that you can notice is that the turbulent viscosity for the K omega SST turbulence model is larger than the K omega SST turbulence model. So that kind of covers all of the topics that I wanted to cover here. We've kind of looked at the experimental fixture setup. We've reviewed the expected flow structures. We've reviewed the predictions of 4 CFD predictions using 2 different software tools, 2 different turbulence models. And I would say that these predictions show us that we can actually do a really good job of capturing these flow structures and these temperature gradients for engineering purposes. Near the wall is probably the more questionable area, but in general, I'd say that both of these tools, all of these tools, do a really good job of capturing the flow structures for making engineering decisions. And lastly, we kind of talked a bit about this turbulent viscosity and how it really is used, where it comes from, and how it impacts the predictions that we make in this particular benchmark. So that covers it. If you're really interested in more technical content, there's quite a bit of it here. I would encourage you to go to the Azore CFD website. At that website, there's more tutorials, webinars. You could also get a free 30-day trial of Azore if you're interested in exploring using Azore. And go down. This video is on the Azore's website, their YouTube channel. So go and subscribe there so you don't miss any more content.